next speaker is Edgar, and if I read the title correctly, we will have a slight change of topic now. So we will hear about the Bayesian methodology for hybrid degradation prognostics.
All right, so thank you very much. Thank you for the introduction. And so, yes, quite a change of topic. I'll try to make it, hopefully everyone will find something interesting for themselves. This is a slight change from my original plan for this conference. We'll be mentioning a little bit conformal prediction, but at the very end. So we'll not be totally off topic from everything we've heard before. Okay, so of course, first I would like to thank the organizers for putting up this. It's been a great conference so far. So I'll be talking about this Bayesian methodology. So we've heard about Bayesian calibration during this conference, and I'll explain a little bit what I mean by it. And with a specific application, which is called here degradation prognostics. Now, why do we mention this application? Sorry, is this working? So as a backdrop to this whole presentation, so we're working with Électricité de France, which is the French utility company, and they own all the nuclear reactors in France. And so they're interested in in management of their, say, maintenance planning of their components. And so in a nuclear reactor, we have, so it's a big boiling kettle, as you might imagine, and there's one component, which is the actual kettle, called the steam generator, in which the heat from the nuclear reactor was transferred through tubes to a secondary circuit, which we see here in blue. And over long periods of time, so like 10, 20 years, we get these deposits, clogging deposits, that, well, basically they're not very good. Well, they exist, and all we can do, that they may require some chemical cleaning. It is not a nuclear threat, so don't be afraid. But it undermines performance and can weaken the structures. We wouldn't like to replace the components. So requires chemical cleanings means maintenance planning. And so how do we do maintenance planning? So the idea is that we try to develop models. Now, models means computer models or simulation models or data-driven models, purely data-driven. Now, so far as simulation models go, there is no state-of-the-art solution to today because of the complexity, as you might imagine. So it's long periods of operation, and it's also very hard to model and reproduce a proper lab experiment of clogging of these steam generators. There's also not a lot of literature. Now, if we want to access data, we have a few amounts of points that are made basically during when we stop the nuclear reactor, so that doesn't happen every day. So these video data are scarce, so we don't have enough data to probably, I don't know, build a neural network, for instance, something you might like. And now, so far as, well, physical models without maybe entire precise validation, we have physicists that work on this and that have developed a model, a computer model called Peak Buffer Depot, which is an aggregate of a certain numbers of submodels. Now, with all of this, we have to make some predictions, and the idea is how to make use of all of these tools to achieve reliable predictions. Now, to get a bit more general and understand why we talk about prognostics here. So as I mentioned, in that industrial system, it could be something else. At the moment, it's steam generators, but it could be bridges, components, and more generally, now we're interested in something called digital twins. So we would like to use all of the information that we've got and to monitor more or less the assets. Now, these engineering components, they require, well, they degrade over time, so there's a need of maintenance, and especially for critical applications. And when we say prognostics, if delta here is the degradation level over time, we're interested in evaluating this, which is basically the threshold after which we've determined. It could be, of course, I've written it like this in a scalar way. It could be more complex then. But the idea is, what is the time remaining until your system reaches a certain specified threshold, where you know it's either conservative enough to make sure that the system doesn't break up, and how do we evaluate the degradation level? So we usually rely on physics-based simulation codes and data-driven, as I said. Now, if we use individual approach, if each individual approach is not robust enough, the idea is that, so first there's a high level of uncertainty, epistemic, aleatoric, but also individual predictions are not fully reliable. So also to give some more notations now to get to the methodology I've been speaking about. So let's assume we have a physics-based computer simulation model, which basically has some inputs and gives us a time-varying output, but gives us the whole trajectory of, say, for one input, we get the whole trajectory of degradations or whatever it is. And now at each time, so which I denote by a projection here, we approximate the degradation level at that time. Computer models are expensive, and so we assume we have some surrogate modeling strategy. I'm purposefully vague a little bit about that, but the idea is to approximate the code with a less computation effort. And now this is the interesting thing, which is, well, we don't have just one type of data. We have what I call heterogeneous groups of data. Meaning that, so for instance, in our asset, we have either different sensors that are measuring the same thing, different manufacturers that build those sensors, or for instance, different operators that then stop when they do the actual measures and they don't do it the same way. And so we have different varying sizes of these data points that arrive at different times, and we suppose that they are so homoscedastic between them. So we have Q groups like this. Each of the groups are heteroscedastic between those, which we can see here that the variance is different for each group I. And so how do we mix all this up to get a reliable remaining useful life prediction? So maybe you've heard about data assimilation. We haven't heard a lot about it during this conference, but basically it's still a Bayesian method where we work iteratively in time. So we have a model that evolves in time. And we usually work with Markov chains, where here iteratively we update the model by just so pushing forward and then updating and pushing forward sequentially like this. And this is the state of the art what one could do in this setting for prognostics. Now, here we have some scarcity of data, where they're packed in groups, and we don't have new points that arrive on the fly, which is usually the case in data assimilation, for instance, in weather forecasting. So it's what maybe we would try to do something which is rather offline, called offline data assimilation, and that resembles a lot Bayesian calibration of computer models. Because the objective is to estimate this posterior distribution given the groups of data of, again, influential parameters within our input parameters of the code. And at the end, we push forward once we update these priors. Through the computer model, we push forward these updated measures, and then we evaluate this as our probabilistic remaining useful life. We find a CDF that is conditioned on the groups of data. And we hope, that's the idea, that this probabilistic rule, our remaining useful life, will be better for decision makers than what would happen if, say, we didn't have the YIs up over there. Okay. So that's it for the setting. Now, if we get into what actually we're proposing as a method. So looks a little bit, lots of notations, but I'll try to break it down in different steps. So this is an iterative method. We're in a setting where we don't know very much either because our computer model is not valid. I mean, it is valid, but it's not entirely valid. There's uncertainty. And so we know we have some uncertainty in input parameters. Now, how do we assess, first of all, those input parameters? So step one, we start off with a uniform distributions on all the D parameters of the computer models. These uniform distributions are assumed to be independent. This is important, really. Really, independence is core in this whole methodology. We want to have independence on all the marginals, so to assume as little as we can. And we generate, you choose your sampling strategy, there's a design of experiments. And with this first DOE, so we start at iteration 0, and we go up until iterations D, we compute what we call sensitivity indices. And this, we have chosen specific sensitivity index, which is based on kernel methods called the Hilbert-Schmidt independence criterion. Now, why is this interesting here because it works in a given data. So we have to do this push forward, this first sampling of points. And if we have a limited computational budget, or say we have an engineer that just gave us those, maybe we have 100 points, then, well, HSIC is very nice because it works in given data settings, and we can achieve some really interpretable, we get some interpretable results just with these estimators. And it allows to assess individual contributions. As compared to, maybe you've heard of SOBOL, but okay, you have like interactions. Here really we're working with one specific input. And so that evaluates the individual influence. Now, once we've selected, because, okay, we rank our variables using this sensitivity. So we have the D variables that are ranked at step K. And we choose the maximum, which has the most dependence on the uncertainty. And then we have a surrogate modeling strategy. And now we want to be as little biased as we can. And so this is usually also a problem we've heard about, specification and Bayesian calibration. And well, here, since maybe, again, we are provided surrogate models, or we build them, but we're afraid of misspecifying the priors or stuff like that, or we just assume we have a bunch of them. And with these P meta models, we will aggregate them. And so with the GAG you see there, we vary in the maximal direction of sensitivity. And that will be the one which we will calibrate using something I'll tell in a minute. So how do we do this? We have a specific Bayesian Bayesian likelihood setting and whatever. And we have a MCMC sampling procedure, which is random walk. And in order to close the loop, we need to evaluate some, so did our priors get informed in any way? And so we evaluate the Kullback-Leibler divergence here, because, well, it is a measure of information. And if the uniform, so now this is the trick move. We choose an epsilon here. If you know how to, like, interpreting values of measure distances on over probability measures, I'm interested, because for the moment it's pretty empirically calibrated. The epsilon, we update the prior because we say that our marginal, well, has been informed well enough by the data, and then we continue. We proceed that way, and so we evaluate a new input, and so on. And if well, we arrive at a step where there's no new information in the data for that specific input, then we stop and we do our rule estimation by pushing forward that measure that we come up with. So what's important is really replacing the marginal with the posterior distribution in the case where there's information. Now, about the updating step, and this is where we have this the multiple data groups that are found. So we do a little transformation. So we want to integrate the uncertainty on the noise. And so we use a specific prior on that transform, and we use the Jeffreys prior also for the for that. And finally, this formula 3 generalizes well when we use what I've called these heteroscedastic groups of data, because, well, if they're independent somehow, now we can generalize this posterior up to a constant probability density function to the product of all of those differences in norms. And so this is useful if we want to estimate or take the log, or we'll do some little information. So this, what are the proof for this is in our paper, but it's very simple, just some Bayes theorem and simple simplifications. Now, okay, so we still have a conditioning here on whether at step K we have the other the nominal variables of the latent, so d-1 variables there. So we don't only condition on the y1, yq, but also on the other ones. So we basically just take the mean at that step. And we want to integrate, so if we do this convex aggregation I've mentioned, we want to integrate the uncertainty, and so what we do some Monte Carlo integration by using a Dirichlet distribution. And finally, when we use this as the the target probability, log probability, because we also do some numerical tricks. The target log probability in our random walk Metropolis Hastings, we, well, basically get good results. And we test these results by launching multiple chains and testing the Gelman-Rubin statistic. But there is still this conditioning here that we don't like, and so that's future work on how we might integrate this uncertainty. It doesn't work by just sampling and giving some Monte Carlo stuff. But we still have priors on that U0K that we can use, but we still don't really know how to do it. Okay, and to get back on my original say application, so we have this complex code that does exactly what I said, which is a chaining of a number of codes, and we simulate clogging kinetics over 60 years. Now, we have two data groups which correspond to what I call the field data, which are actual measurements, and then more like regression data, but that comes from, say, they've developed models and found in transients in the different operational scenario and managed to more or less work the inverse problem to correlate the clogging rate with it. And with these two data groups, okay, we use them as the Q equals 2 groups. And we have a probabilistic modeling. Okay, now you see these names of variables. I'm sorry, I'm not giving all the details. It would take too much just to give the model. We have a paper if you want to look it up. And this is what the results look like for the posterior distribution. So we have 12 meta models here. Monte Carlo Mark 5 MCMC change launched at every time. And so why do we see 3 histograms every time? Because we have 3 different scenarios. And so we see that 5 out of 7 of the distributions are informed by the data. And we get these distinct modes for AV, which is pretty interesting because that's, at least the ones that developed the model found that this is really something that drives the kinetics, and it varies following the maintenance scenario. So we were happy with these results. But more importantly, when we get to the trajectory, so here you see how clogging rate varies over 60 years of simulation for one specific steam generator. There you see the data, how it looks like. So it's pretty scattered. So we see that this had a whole pack of uncertainty at the beginning, and then we've reduced the spread of the trajectories. And more visually, if we look at the last, so at the last setting over here, this is what was the prior remaining useful life. How did it look like? And now we see that we've substantially reduced the uncertainty, but we have also pushed the mean to the right, which is, we're not just tricking to help the models, but this is actually informed by the data. As we can see, the data points provide something very different from what the computer model does. So this is a positive impact. Okay, so I'll skip the summary. Hopefully you've understood all that I said. But just to say a word about conformal prediction. So this, so we've done some work concerning Gaussian process surrogates and how we can use conformal prediction in this case. So I refer to you, in fact, you could go and see Aurelien's poster. He's worked upon this, and it's very interesting. So we are giving a computer model surrogate. So we have a deterministic computer model. We do a GP emulator of this. We know we have Bayesian credibility intervals. But now there's always the problem of well specifying the model. Now, conformal prediction has the nice flavor of not requiring any hypotheses on the model. So also we have one of the variants of CP that works with small amount of data. That is the Jackknife Plus, as Emric was mentioning this morning. So in the Jackknife Plus cross-conformal setting, we've used the posterior GP, so after we have learned from the data, to construct these adaptive conformal prediction intervals. So they're adaptive, meaning they vary in width. And what is even more interesting, and that we would like to do, but that's still work in progress, is how can we perhaps use this varying width as a proxy for surrogate accuracy? And using this accuracy, perhaps we could add some active learning step in the MCMC procedure, and that would be very nice. Now, if you want to talk about this, I'll be very glad. So thank you again. Here are some, so that's the article about what I've said. If you want to talk about CP and Gaussian processes and some GitHub. Thank you.
We have time for a couple questions. Everyone's hungry? Well, then let's thank all speakers of this morning again.